Our speaker today is Marie Svane, who will be telling us about analyzing point process using topological data analysis.
Yes, thank you very much, Teresa, for the invitation to speak here and to present my work to a different audience that I'm normally speaking to. So I'm usually working in point processes, but I'm particularly interested in what happens when you apply topological data analysis to point processes. So I'm assuming that you are somewhat familiar with the topological data analysis, but maybe not point processes. So I will start by an introduction to point processes and which kind of questions we're interested in regarding point processes. So I'm going to spend some time on that. And then look at what happens if you apply topological data analysis to point processes. And then I'm going to show you some results. And finally, if we have time, I will show you a short data example. Okay. So starting with the point processes. So a point process P, that's a random set of points, which is almost surely locally finite, meaning that inside any bounded set, there's almost surely going to be only finitely many points. And here in the bottom, you can see 3 different realizations of point processes. And they're generated by different stochastic models. And if you look at the 3 pictures, you can maybe see some differences here. The first pattern here, the points are completely independent of each other. So they're just randomly scattered in this squared. In the second picture here, we have some clustering. If you look closely, you can maybe see that the points, they're very often lying like 2 or 3 points at the same spot. So whenever you have a point, there tend to be more points around it. So this is a typical model in, for instance, plant ecology, where a plant, so the points could mark where a certain plant is growing. And since it tends to spread its seed around it, the plant will grow in clusters. So that could be a model for that. In the third picture, we have a point pattern that looks more regular. So in this model, the points tend to repel each other. So you could, for instance, think of particles in a gas that don't like to be too close to each other, so there will be some repulsion. And then you might see a point pattern like this. And so what we're interested in is some methods to distinguish between such different point patterns. So first of all, we will make some assumptions on our point processes. So we will assume that the point process is stationary, meaning that the point process itself and the point process, if you translate it by some vector x, you have the same distribution. So it will mean that this point pattern will look the same everywhere in space. So for instance, if you think of the particles in a gas, it seems like a reasonable assumption that it looks the same everywhere in space. But for other things, for instance, if the points mark disease cases, then it's likely that there will be more cases in highly populated areas. So the distribution will not look the same everywhere in space. So in that case, stationarity is not a good model. But it will be the assumption throughout this talk. And when we have stationarity, we can talk about the intensity. So if you look again in a bounded set B, and you count how many points there are inside B and take the expected value of that, so the expected number of points inside B, well, if you have stationarity, then this will just be a multiple of the Lebesgue measure of the set, and this multiple rho is what we call the intensity. So it means that the expected number of points in in a set of unit volume will be exactly rho. So that's the interpretation of the intensity. Okay, so I'm going to now introduce some of 3 different models for point processes that generated these 3 pictures I showed you in the beginning. And the first one was the one where the points are completely independent of each other. This point process is called the Poisson point process. So its definition is as follows. If you have a bounded set B, then the number of points inside that set will follow a Poisson distribution. And the parameter of that distribution is the intensity times the volume of the set B. So this ensures that you get the correct expected number of points. So that's the number of points. And once you know how many points there should be inside B, then so if that's n, then the distribution of these n points are just independent of each other. So the number of points is random, but given the number of points, when you know it's n, you just throw in independent points in B, and that gives you the point pattern. And this Poisson process has this nice property that whenever you take 2 disjoint sets, B1 and B2, and look at the point process inside these 2 disjoint sets, then that's going to be independent of each other. And in fact, this independence property in disjoint sets completely characterizes the Poisson point process. So it's the only point process with this property. And that's why we think of it as the natural model for complete spatial randomness, because you have this independence in disjoint sets. Okay. So that was the first picture I showed you here. So the second picture that comes from a Poisson cluster process. So it starts as before with a Poisson process, so where you just have complete spatial randomness, but then each point in the point process, you replace it by a cluster. So instead, and by a cluster, I just mean a finite set of points. So each point you take it away and put a finite set of points instead. So you can think again of these plants growing, the Poisson process being the parent plants, and then this new cluster is then the offspring of the original plant. One way of generating these clusters is, again, you take a ball around your point, and then inside that ball you generate a Poisson process. So you get random points set in that ball, and you can use that as your cluster, for instance. And that's the kind of model that generated this picture down here. Okay, so the third example, it's an example of a Gibbs point process. And this is a model that comes from physics, and it's most intuitively explained in terms of an energy functional psi. So if you have some finite configuration of points, then you can associate to it an energy. And the idea should be that if the energy is high, then your point configuration is less likely to occur compared to a Poisson process. Okay, we assume that this energy is something positive. It's increasing so that if you add more points to your point configuration, then the energy will increase. And then it should be translation and rotation invariant. So if you translate or rotate your point pattern, then the energy should not change. So that's all very natural assumptions to have. Then there's a second assumption also, which is very important. And this is, well, for us, and that is that we have finite interaction range. So that means that if you have a point pattern, so these black points here, and you want to add the red point, then the energy will increase, and how much it increases only depends on the points inside this little ball. So we say that the point the red point here doesn't interact with the points here outside the little disk. And it's important when we work with it that we have this finite interaction, because it becomes very hard to control if point can interact with each other when they're very far away from each other. Typically, physicists would want to have a large interaction range, but we will assume that it's finite and also below a certain bound where we have good control over things. Okay, but then the idea is that the Gibbs point process, if we look at it in a bounded set B, then it has a density with respect to the Poisson process that has this form. So this set of B is just a constant. And here you have exponential minus beta and then the energy of your point configuration. And it means just that when the energy is high, this density is going to be low. So this point configuration is going to be less likely than it would be under a Poisson distribution. And then I didn't give you, so this is, you don't need to remember this definition. And it's not even the correct definition, because actually this definition doesn't extend to a point process on the whole unbounded space RD. So you have to be a little bit careful how you define this. But it's anyway, it's this idea that you have an energy of your point configuration, and when this energy is high, your configuration is not so likely. So here's just the most simple example is that we set the energy to infinity when there are 2 points in the configuration that are closer than R0, and otherwise we just set the energy to be 1. So when the energy is infinite, it means that the configuration cannot occur. So it means that we cannot have configurations where 2 points are closer than R0. So this is what we call a hardcore process, because you can imagine that the points are actually balls of a certain radius, R0 ½ There's a softer version called the Strauss process, where the energy is proportional to the number of pairs that are within distance R0 from each other. So here the configuration is punished for having many points that many pairs that are close to each other, but it's not impossible. And that's the kind of model that generated this third picture over here. So here the points do not like to get closer than a certain radius R0, but it can happen. Good. So these are kind of the models for point processes to have in mind. So now I go over to something more familiar to you, hopefully. So that would be the topological data analysis part. So here we start with a point pattern, and now we don't assume any random noise. We just think of a fixed point pattern in RD. And so we have points. We start with the point pattern here, and then we grow balls around these points and see how the topology changes when we grow these balls. The way we measure the topology is by homology groups with Z mod 2 coefficients. If we call XR this union of balls of radius R, then for 2 radii, R1 smaller than R2, we get a map of homology groups, and we can do that for increasing values in R and see when this homology group changes. And if these points are in general position, which they will be with probability 1 for all the point patterns I will look at, then the dimension of these homology groups can only jump by 1 at a time. And when it increases by 1, we say that homology class is born, and we say that homology class dies if the dimension decreases by 1. And if you're a bit careful, you can pair these birth and death times. So you can talk about, well, the birth and death time of a homology class. And this slide is just to give you an idea about why we could be interested in this. So remember these point patterns, we were interested in clustering of the points. So when we grow these balls around, at some point they start merging, and you can think of the connected components in these pictures as clusters of points. And then when we increase the radius of balls, we can imagine that we're measuring clusters at different length scales. So these connected components should have some interpretation as clusters. And well, the connected components are measured exactly by H0. And in 2D, we also have H1, which measures the connected components in the complement of the balls. And that gives us an idea about then how, well, so connected components in the complement that corresponds to large empty regions in between the points. So here you can see, for instance, that there seems to be a large empty region between these points here. And over here in the last picture, you can see a component that has formed here, which has a relatively large lifetime. So large empty regions here will be would correspond to a birth-death pair with a large lifetime or life-death time. So that also gives us some relevant information about the point patterns. So then in higher dimension, you also have the homology groups in between the H0 and HD-1, and the interpretation of them for point patterns is more difficult, but it still captures some information about the point pattern, so they're still worth looking at. Okay, so these birth and death times, we summarize them in a persistence diagram where we plot the birth time on the x-axis and the death time on the y-axis. So here it's done just for this small point pattern I had down here or over here. And this is for H1. So you see that's 1 point with a large lifetime, and that corresponds to this void in between the points down here. Then we can look at if we apply as topological data analysis to these different point patterns I showed you in the beginning, and we can look at what the persistence diagrams look like for these different point patterns. So again, this is done for H1 here. So first we had the Poisson process where we have complete spatial randomness. So that's kind of the reference point pattern for everything. And you can see what the persistence diagrams look like down here. And for comparison, if you look at the clustered point pattern here, we seem to have more points up in this region here with large birth and death times. And that corresponds to these larger empty regions in between the points. So I have the same intensity in these two point patterns, so the same expected number of points. So since the points cluster together, then in between the clusters, there will also be more space. And that's what we see with these points up here. And then we also seem to have less points down here with low birth and death time corresponding to that these clusters. So there are not so many classes born at very early time. So it seems that these points in the clusters do not really form anything in homology at a very small birth and death times. And then we've had this finally this repulsive pattern, which if you look at it, it looks more regular than the two others. And you also see that the points in the persistence diagram seems to cluster more in the lower end. So points seems to be born and die at similar times, which somehow captures some of the regularity here. So there seems that there should be some information about the point pattern in these persistence diagrams. So we could so we could be interested in using them for statistics. And for that, we want to have some quantitative, so this, we have this two-dimensional diagram, but we want some quantitative summary of the persistent diagram. And one way of doing it is via the persistent Betty numbers, which I also learned from Yossi recently. They're also called rank functions sometimes. So maybe this is the more correct name. I'm used to calling them persistent Betty numbers. But what they are is that so I call them Betty beta BDQ. And that's, if you look at homology Q of XB, and then the image of the map to the homology of XD, and take the dimension of this, then you get the persistent Betty numbers. And the way you find them from the persistence diagram is you find the point B, D in the plane, and you draw a square with B, D as the lower right corner, and then you just count how many points there are in this square. So that gives you the persistent Betty numbers, and you can do that for all values of B and D, and then you have in total the same information about the persistence diagram as in the diagram itself. And they're convenient to work with because they have this algebraic definition. Okay, so assume we want to do some statistics on topological, using topological data analysis. And we have observed this point pattern P. And then we might be interested in the null hypothesis that this point pattern comes from a certain point process model. So this could be one of the three models I showed you in the beginning. So what you typically do in statistics is you compute a summary statistics. So some number that you can compute from your observed point pattern. And one simple idea could be used to use one of these Betty numbers, computed from your point pattern, and then compare it to the expected value under your null model for a fixed choice of B, D. So then you would have to come up with, in advance before you do your analysis, a good choice of B, D that tells you the thing you're interested in about your point pattern. This may, I don't know, it's not obvious how to choose them if you're just like in advance. And also it may not be the thing, really the thing you're interested in. Like if there's a specific part of your persistent diagram that you think capture the information, then you want to look at that somehow. So you could try other things. You could also look at these persistent Betty numbers now as a function of the birth and death time. So now they're a whole function, and let's say that we look at them on some bounded square in the plane. And then you could consider this function and compare to what it would look like under the null model. So that's maybe also going to be, I mean, if you want to look at this as a function and compare to the null model, it's probably going to be quite computationally expensive to do this. So you could also look at other functions of your persistence diagrams. For instance, you could look at a sum over all birth-death points, and then you take a function f of the birth-death pairs. So that could be anything, but it could, for instance, be an indicator function for some region in the persistence diagram that you're particularly interested in. You can count points in that region. You probably know better than me what is a good choice here, but it could be, in principle, many things. You could also look at one-dimensional summary of the persistence diagram, such as this accumulated persistence functions. So this is now a function of R, and what you do is you sum all lifetimes, def minus birth time, for all pairs that are born before time R. So this function was actually the original motivation for this project. It was suggested by my co-author, Christophe Biscio, together with another colleague from Aalborg, Jesper Møller. Yeah, so you could use any of these summary statistics for your statistics, and then it would be possible to do the statistics without assuming any distribution on your summary statistics, just by simulating a lot from your null model and then comparing. But it may be intense computationally, so you can make things a lot easier if you have know something about the distribution of your summary statistics. And what we do in statistics is typically we derive some central limit theorem, which tells us that if you have enough data, then your summary statistics is approximately normally distributed. So that's the kind of results I will aim for. So as I said, these results, they typically hold only when we have enough data. And very often in practice, when you have point processes, we only have one realization available. If you have many realizations, then the standard tools for central limit theorems apply. But if you only have one realization, what we mean by enough data is that we observe the point process in a large window. So here I will let Wn be the observation window. And for simplicity, we will just assume that this is a cubic window of volume n. So what we can observe of our point patterns is just the points that are inside this observation window. And then we can look at the limit when the volume of this window goes to infinity. And the first thing you could ask for is, if we look again at these persistent Betty numbers, you can ask, do they converge when the window goes, or when the volume of the window goes to infinity? And this has already been answered by Hirsch, Girai, and Trin. They have shown both that if you take the expected value of the persistent Betty numbers and divide by the volume of the window, which was n here, then they converge to some constant. And actually this convergence to the same constant also holds almost surely. So if you don't take expectation. So this is known. Then how about the distribution when n goes to infinity? So this has been shown in the case of a Poisson process, first by Jokic, Subak, and Adler, in the case where birth and death times are equal, and it was generalized by Hirsch, Girai, and Trin. So the result here says that the persistent Betty numbers minus the expectation divided by the square root of the volume of the observation window converges to a normal distribution. So in a ongoing project, we are working on generalizing this to the case of the Gibbs point processes that that I showed you in the beginning of the talk. So these were the repulsive point processes. So here we can get a similar result, and we can also show that if the energy is always finite, so meaning that we don't have these configurations that are not allowed to occur when the energy is infinite. So if we don't have that, then we can also show that the variance in the limit is positive. So it's actually a non-degenerate normal distribution that we get in the limit. So then there was the next suggestion was to look at the Betty numbers not just for a fixed value of birth and death times, but look at it as a function of B and D. And there you can also get a central limit theorem. So now we think of this quantity, so the Betti numbers minus expectation divided by the square root of the window. We now think of this as a function of b comma d in some bounded region of the persistence diagram. And then the claim is that this now is a stochastic function, and it converges to a Gaussian process. So now the convergence is in a slightly different space, the scorecard space, which is a sort of space of cat-like functions in 2D. Anyway, so it requires a bit more than just the individual convergence of these Betti numbers. But the results we have here are quite limited still. So they are restricted to 2D. And also we have to destroy the topology a little bit. So the topologists are probably not going to be so happy about this. At least I'm not so happy about it. But we have to modify these Betti numbers a bit so that we automatically kill a component if its diameter becomes larger than some m, so some fixed constant m. So the problem is when this ball grows, then the components can become really large, and at some point they become even infinite. And it's very hard to work with this when we have to prove theorems. And so we have to somehow artificially create a bound on the spatial diameter. And yeah, it's not so satisfying, and we still hope that we can find a way of getting rid of this imboundedness. So I can just mention here in the bottom that there has been some updates on this by Magnus Bagge-Botnan and Christian Hirsch in the Poisson case, but they still have to one way or the other modify this model a little bit. So we can't just have the standard Betti numbers, because somehow we can't get the proofs to work at this stage. So that's where we are. Okay, so but what is then the good thing about having such a functional central limit theorem?
Sorry, can I interrupt you for a moment? Because
yes,
there has been a question.
Yes.
What does cat-like mean for a function defined on the square?
Yeah, yes, this is a good question. So it's something like you have limit in the axis parallel, or you have the limits from the left and continuity from the right in the axis parallel directions, so more or less. So the Betti number as function will satisfy this. Was it okay? Okay. Yeah. So what is the advantage of having a functional central limit theorem rather than just for the individual Betti numbers? Well, the advantage is that we can use it also to derive new central limit theorems via the continuous mapping theorem. So that says that if you apply a continuous function now in scorecard space, then you also get new limit theorems. And for instance, I showed you this accumulated persistence function before, where you sum all the lifetimes up to a specific birth time r and consider this a function of r. So this is now a one-dimensional function, and you can get a new central limit theorem out for this. So this again converges now to a one-dimensional Gaussian process. Yeah. And I mean, you can, in principle, do the same for other summary statistics of your persistence diagram that you may be interested in. Okay, so finally, I promised to show you a data example. So this is a data set from neuroscience. So it was collected by the lab of Jens Nyrengaard in Aarhus, and they have images from a brain, and the points in the point patterns marked where certain neurons are in the human brain. It was a 3D image originally, but here it has been projected to 2D. And the hypothesis behind this study was that the neurons tend to arrange in vertical columns in the brain. So the idea here would be to project these neurons from 3D to 2D, and then these columns should be projected down to clusters in the two-dimensional image. If you have more points or less over each other and you project them down, then you get a cluster in 2D image. So we would like to see if we can detect some clustering in this image, or at least some deviations from complete spatial randomness.
There has actually been a question about what you were talking about before, I think. Namely, David is asking, I'm thinking that both the persistent Betti number for a point pattern and the estimated Betti number of a point pattern reduces to the same form with a fixed birth and death. But with the Poisson case, I am quite confused. Could you explain further? It sounds a little bit like a question that might make sense to just discuss in the end if you don't want to.
Yeah, maybe we can wait. So
yeah, okay.
Yeah. Okay. So I mean, I just show you here the next slide. So here we have the persistence diagram for the data set, and on the right you have the persistence diagram for the Poisson process. And if you just look at them, well, they look a bit different, but it's hard to tell just by looking at them whether it's really a difference or whether it's maybe just due to chance. So here we have plotted the accumulated persistence function. The red curve here corresponds to the Poisson case, and the blue curve is the data set. And you see most clearly the deviation in H1 here. The data set is somewhat below the red curve. And we made a test for whether this blue curve might come from the same distribution as the red. And you can see we get very low p-values. And these p-values are just computed by evaluating the function at a single point. And then to do that, you need still the expected value under the null model and the variance under the null model, and these are also computed by simulations from the null model. So you still need to do some simulations from the null model in order to do the test here. And that was the talk, and I have some references here. What I mentioned more or less, and also a couple of references to some of the work in point process theory that we're relying on, because there's a whole machinery already to derive central limit theorems, and we're drawing a lot from that. So also been important for us. Okay, so thank you for the attention. And questions.
Yeah, exactly. Thank you very much for this very nice talk. Let's please all unmute ourselves so that we can clap together. Okay, who has questions? Maybe David, for example, you can just, if you have a working microphone, just tell the question that you already posted in the chat yourself. Or maybe someone else has a question. Just go ahead.
Yeah, so I'm just trying to understand. So you have the Betti number for a point pattern and the estimated Betti number for the point pattern reduces to the same form. So I'm not completely sure I understand the question here. So I mean, the idea is that the point pattern is random. So we want to compare the the Betty numbers from the realization that we see to the expected value. So like the average of overall realizations of this from this point process model. I don't know if that's what you refer to here. Or
yeah, thank you, Anne-Marie. I think like if David doesn't feel satisfied with the answer, then maybe either voice your
yeah, I just feel free to.
Exactly, either by writing or by just unmuting yourself and speaking.
Hello?
Yeah, we can hear you.
Okay. So I think before the page before the Poisson case, I think the page before the Poisson case, you made an assumption there that if you have the Betty numbers on the Poisson the point pattern, it reduces to a form that converges to the same form when it's on the estimated process pattern, the point pattern.
Wait. Yeah, let me just. Where was? You're thinking of this one?
Yeah. No,
yeah.
Not this one. The next page.
One. Yeah, this one.
Yeah. But I think the page, the limit on it, you put a limit on it and it reduces to the same form. That is for the 2017. I think that was 2020 or 2017 before you came to this page. The theorem, then I think go back, one page back.
Yeah.
So I think this theorem, the 2018 theorem.
Yeah. So this is, this is just, are you thinking about this, the difference between this theorem and the next one?
Yes, please.
Yeah, okay. So here you're scaling by 1/n. So this is like your average. So you compute Betty numbers from the whole window and divide by the volume of the window. So you can think of it as a kind of average Betty numbers in your window. Here we're only scaling by the square root of n. So that so in that case we don't really get convergence here. So it will still, this quantity will still fluctuate and in the limit by a normal distribution. Does it make sense?
I was thinking maybe because the average is constant, that doesn't matter even if you take the average, because the average is constant for both patterns. That's for the Betty numbers of the point pattern and the estimated. You are using the same average.
So here, the square root of n, this is the magnitude, so to say, of the variance. So what the standard deviation. So what we're really doing here, we take the summary statistic minus the mean and divide by the standard deviation. So we expect to get something that has a non-trivial distribution.
Okay, thank you. Then there's another question, namely about this brain data set that you had. I think it's kind of about getting a resolution for it. Like, did you find in the end a point process amongst the examples you consider?
No, I mean, we didn't really try so hard to find something, but it's a good question. Of course, you could try to search for a model where the persistence diagram fits, but we didn't try it in this data example.
Okay, thank you.
I'd like to ask a question. So these are two examples where you have convergence to a normal distribution here, but you had at least one example where you converged to something that wasn't a normal distribution. How do you come up with those limiting distributions? Do you do a bunch of simulations to form a guess, or is it sort of like somebody proved a related result in the literature?
It's very, very often instead things. If they converge to something, it's a normal distribution. So, I mean, it's just always a standard guess, and there's a lot of machinery done in point process theory for how you derive these theorems of the form that says something converges to a normal distribution.
Uh-huh.
And it's nice if we can get something to converge to a normal distribution, then we have a distribution we know and know how to work with. So we also like to have that kind of results.
Yeah.
So, yeah.
So it's less simulations and more knowing the theory and knowing the related results.
Yeah.
Mm-hmm. Thanks.
There's another question in the chat. Are you aware of a connection between the persistent Betti number of a point set and the discrepancy, star discrepancy or LP discrepancy of the point set?
Yeah, so I'm not sure exactly what is the star discrepancy or LP discrepancy.
Maybe
so
Alexandros, you can also try to
maybe
explain
you can, if you want to elaborate.
Yeah, sure. Sorry. Can you hear me?
Yes.
Yes.
So discrepancies considering considering axis aligned boxes that you grow them and then you take the number of points falling in these boxes minus the volume of the box, and you integrate over this difference of the volume of the box and the number that fall inside the box. And you integrate over all like possible boxes in your region. So I was wondering, it feels like there is a connection, and I was wondering if you were aware of one.
Short answer is no. So maybe so I mean, you're thinking then these boxes now in the point pattern, like trying to divide this. Yeah. Yeah, so I mean I don't know these concepts, but I mean I know these stability results and so on for persistence diagrams, and somehow it doesn't really apply here because the randomness involves the whole space. The points can move around the whole space. So I don't know if these things I mean I can look into it, but yeah, I don't know if it is helpful.
Okay, thank you. Thanks for the talk.
Oh, there's already the next question in the chat. Sorry,
you
want to say?
It's a guideline to choose good set of pairs B, D. No, and actually I think this is the problem if you want to use the Betti numbers itself for summary statistics. And actually we had the same problem I showed you in the data example where I said we evaluate the function at one point, but we have to choose a good point before that makes sense. So I mean you should, so the guideline is you should choose B and D before you do the analysis, and maybe you don't really have a good idea of what is a good B and D because before you have seen the persistence diagrams, but they should somehow come from your intuition or like what part of the persistence diagram do you think is interesting. But I mean, you can also from some of these limit theorems derive central limit theorems for other summary statistics. Let me see, why did I have this? For instance, we also have a central limit theorem for something of this form, where you have function of a sum over persistence pairs and then a function of pairs B, D. So that could like capture be a function that captures the region of the persistence diagram, which you expect to be most relevant.
Thank you.
Okay.
Okay, then maybe we have enough questions now for the public part. Thank you very much again.
And thank you for the questions.